Hello and welcome back to another tutorial for the TI-84 Plus. Today we're going to be talking about how to do hypothesis testing with your TI calculator. Now keep in mind that the TI calculator only helps with finding values for the hypothesis test. Analyzing the hypothesis test, just like analyzing confidence intervals, is up to you. I am also going to remind you that before we do any hypothesis testing, whether we're doing hypothesis testing on proportions or if we're doing hypothesis testing on means, that there are conditions that need to be checked. I'm going to have those on the screen for a second now so you can see those. If I'm doing hypothesis tests on proportions, need to make sure it's a simple random sample. That's n times p sub 0, which we'll discuss what that means in a moment, times 1 minus p sub 0 is greater than or equal to 10. And that we have independent samples, which means the sample is about 5% less than the population. We have similar checks for the mean. The only change is that instead of np1 minus p, we check the central limit theorem, which says that we need either a normal distribution or we need to know that we have a big enough sample size, which typically means more than 30. These conditions should look familiar, particularly if you've already done confidence intervals, because they are the same conditions to use for confidence intervals. The only difference is that with proportions, it's denoted as p sub 0 here instead of p hat. So it's a different proportion to keep in mind. With that said, I'm going to dive into here. I'm going to move away those conditions. We're going to dive into where we have our programs for hypothesis testing. These are going to be located in the same place that the confidence interval tests were. That is, in this test section in stat. So, what we're going to do is hit stat, and we have edit where we would edit lists and things. We go over to this third tab over to tests, and we see all of our listings here. Now, we're not going to use all of these for test, but we did use quite a few of them for interval. And if you notice, interval is near the bottom half. The first half should comprise the test that we need. Now, in this tutorial, what I'm going to be talking about is how to do one proportion test and how to do one mean test. So just how to deal with hypothesis testing when I'm just comparing or try to analyze one parameter of interest. Later on, you can also do a similar process for if you're comparing something like two proportions against each other or two samples against each other to see how the values interact or how different they are from each other. But here we're just talking about one proportion or one mean. Now, if you recall our programs for confidence intervals, that's going to also tell us how to know the programs for hypothesis testing. When we were working with proportions with confidence interval, the program that we used was 1probzint. If we're doing hypothesis testing, we want this fifth option here, 1probztest. When we were doing confidence intervals on a mean, our program was tinterval. That because it was based on a different test statistic. It was based on the t test statistic instead of z. Likewise, for hypothesis testing on a mean, we're going to use t-test. So if you already have the programs down for confidence intervals, just replace the word int or interval with test, and those are the programs you use for hypotheses. To give you an idea of what I mean here, we're going to go down to 1probztest and open this so you can see the parts therein. When I open up 1probztest, what we see here is p sub 0. Now, I said I would talk about this later. P sub 0 should be the proportion that you will see in a hypothesis. When you're setting up hypotheses for proportions, we always will have a null hypothesis, where the proportion should be equal to some assumed value. That assumed value, the one we are testing against in our null hypothesis, should be the same as p sub 0 or p null. So whatever our hypothesis test is, this is the value we're testing against. From there, we have x and n, which refer to part and whole of a proportion from a sample. This should look familiar compared to what we did with confidence intervals. So say I have 10 out of 50 individuals that have this proportion. and I want to test this against estimated proportion of maybe 0.15 or something. So it should have a lot of the similar inputs, x and n anyway. The last input we care about is prop, and we see an option for not equal to p sub 0, less than p sub 0, or greater than p sub 0. This should be indicating what symbol you are using in your alternative hypothesis. Recall that the null hypothesis should typically be set up as equal to something, unless you are doing more high-level hypothesis testing where it can go either way. But if you're doing alternative hypothesis, the one that's h sub 1 or h sub a, depending who you talk to, this should indicate whatever symbol we use there, either a not equal to sign, a less than sign, or a greater than sign. When we're working with that and we have everything set up, let's see, in this case I'll say to see if it's less. I know greater than seems good. 10 out of 50 is about 0.2. So I want to see if this is significantly more than that. We're typically going to calculate, but I want to show you what it does if we were to draw it. It should make a normal curve in just a moment. There we go. It goes rather slowly, but it's going to make a normal curve, what confidence intervals and hypothesis testing is based off. And it will show that this is from one prob z-test, and it will show what the z-test statistic is, or the z-score, and the p-value. Now, when you're doing hypothesis testing, you can either do it by finding the z-score and comparing to another z-score, or the test statistic method. Or you can do the p-value method. I'm going to focus more on the p-value method here. Yeah, so this is what it's doing. It's trying to find, based on some original value, some original proportion, how far away is our value compared to that original proportion. Or when we're dealing with means, how far away our sample mean is from the estimated or assumed mean. Alright, so let's get into a couple examples with proportions so you can see how this would be done. I'm going to be taking a couple questions from the textbook that I use in class. For those that do have me as an instructor, these problems are going to be coming from the textbook in page 446. They're going to be questions 7 and 9. I do these because these are pretty simple setup. They give us the information, and all we need to do is run a hypothesis test on this information. When we get to means, I'm going to do one that's a little bit more in depth. It has more questions there. Okay, so we have for number 7. It gives us that h sub 0, or the null hypothesis, is that the proportion is equal to 0.3. Comparatively, we have the alternative hypothesis, h1, is such that the proportion is greater than 0.3. So what that means is that we assume that the proportion is around a 0.3, and our goal is to show that it is in fact greater than that, and statistically significantly so. With the information that the sample size, or n, is 200, the amount of individuals that have whatever property this is referring to is 75, and our alpha level is 0.05. That will indicate our cutoff, and that will be what we are going to compare the p-value to. If our p-value is less than the alpha value, then that means that we have enough evidence to reject the null hypothesis. If our p-value is not less than the alpha value, that means that we have not shown significant enough results and we fail to reject the null hypothesis. Keep in mind that I'm saying fail to reject and not accept the null hypothesis. You do not accept the null hypothesis. So let's plug these values in. Again, go to stat, go over to test, and we want the 5th option down here. We want one prob z-test. When we open up one prob z-test, we just need to put in our information, starting first with p sub 0. Again, this should come from h naught, or your null hypothesis. In our situation, we had 0.3. And the information we want to compare to that is we have 75 individuals of 200 total, 200, not 2 but point, 200 that have this quality. And we want to see if that's significantly more than what p sub 0 is. Now again, we're going to focus on the p-value testing here, but if you use test statistic, you can also use this program to find the test statistic and move from there. Our alternative hypothesis says that p is greater than 0.3, so we're going to keep it on this third option. If you don't have it already, then go over and hit enter on that. And what we're going to do is calculate this. You can draw it as well if you so please, but calculate should be enough for us. And if you note that everything that we have is presented to us. We have prop is greater than 0.3, so we should be able to compare it to alternative and make sure we did the right one. And what we are given is z, the test statistic. We're given p, which is the p-value. This is not a proportion. Well, not really. This is the p-value we see to see the likelihood of getting something as extreme or more extreme than what we got. And we're also given p hat, which is the sample proportion. Note that 0.375 is indeed greater than 0.3, but we wanted to see if it's significantly so. In this case, since our alpha was 0.05 and our p-value is 0.01, this indicates that we have enough information. Our p-value is less than alpha, therefore we have significant information to reject the null hypothesis, and instead claim that the proportion is indeed greater than 0.3. For number 9, we instead have the information that the null hypothesis is such that the proportion equals 0.55 compared to an alternative hypothesis where the proportion is less than 0.55. And the information we have to support that is that the sample size is 150, we have 78 individuals with this characteristic, and our alpha level is 0.1. Note that the alpha level is larger than it was before. It's 0.1 or 0.10 compared to 0.05. This is a larger alpha value, which means we're being a little bit more generous. If it's anywhere close, then we should be able to reject. Typically, you'll see alpha levels around 0.1, 0.05, or 0.01. So, all we need to do then is plug in our new information. We're going to go in stat, into test, and run program 5 again. In this case, we instead have our p sub 0 value is 0.55. We have x is 78, n is 150, and in this case our proportion is actually less than p sub 0 or less than 0.55 as per our alternative hypothesis. So we need to make sure the second one is highlighted and selected. When we calculate, we're going to be getting some different values here. Again, we check our beginning prop less than 0.55. That does look like my alternative hypothesis. But instead, we see z is negative 0.74 approximately, which means it's only about 0.74 standard deviations below the mean. And our p-value is 0.23. This is much larger than our last one. Likewise, we also notice that our p-value of 0.23 is actually larger than our alpha value. What that means is that it's about a 23% chance of getting something as extreme or more extreme than the value that we observed. With that in mind, that means that we do not have enough information. The p-value is not less than alpha, so we do not have enough information to reject the null hypothesis. Keep in mind that I'm not saying that we accept the null hypothesis. We just simply don't have enough information to reject it. We want to make sure that we don't make any error here. Okay, so that's how we would work with some proportions. Not too bad, and it should look pretty similar to how one prob z int works. When I'm dealing with a mean instead, keep in mind that we're doing one prob z test for hypothesis testing on proportion. But for a mean, we're going to use the second option, t-test. And this is because it's based on a different statistic. It's based on the student's t-test, or student's t-distribution. So we're going to run program 2 here. In this case, we are again given, just like with t-interval, the option of doing data or stats. Data indicates that you have values in a list that you want to test. And what we want to do is also note that we have stats available. Stats will instead say, okay, well, I have the mean, or I have the mean from my hypothesis test, and I actually already have the calculated mean and standard deviation from our sample. So this is if we already have the statistics given. If we just have the data in terms of a list, we can put that list into the calculator and run it with data instead. That we don't need to separately do one var stats to get that information. Again, just like how t-interval works. All right, so what I have here is another question from the textbook that I run. For those in my class, this is from page 457 if you want to follow along. This is question 10. To test the null hypothesis that the mean is equal to 45 versus the alternative that the mean is not equal to 45, a simple random sample size n equals 40 is obtained. And we have a few questions here. A few of these we should be able to do without the calculator. Okay, so A, does the population have to be normally distributed to test this hypothesis by using methods presented in this section, and why? In this case, this is asking about one of the conditions for hypothesis testing. For mean, if you recall, our three conditions are the simple random sample, the sample is less than 5% of the population for independence, and our central limit theorem. This question particularly is asking about the central limit theorem, whether we have a large enough sample size, or if we don't, if we need to know that the population is normal. In this case, though, we see our sample size is 40. That's more than enough. That means we have more than the cutoff is typically 30. And since we have more than that, then we don't need to know the shape of the normal or the population distribution. We still know that the sampling distribution will still be approximately normal. So we do not need to know this because we have a large enough sample size. Now, for B and D and even E, we're going to be able to do all of those at the same time. We should also be able to do C. So we're going to run through B, C, D, and E all at the same time. B gives us that the sample mean is 48.3 and the sample standard deviation is 8.5, and we want the test statistic. The test statistic in this case is going to be our t-value. If we're running proportions, the test statistic would be the z-value. C will ask us to draw the distribution with the area that represents the p-value shaded. We can do that in the calculator as well with most 84s. If not, you can always do it by hand. D says approximate and interpret the p-value. So we're going to look at the p-value and also get that from the graph. And then E says if the researcher decides to test the hypothesis at the 0.01 level significance, will the researcher reject the null hypothesis and why? So we have a few things to do, but again, we can run all of this at once. For t-test, we have the data, so we're fine with this. Our mu sub 0, just like with p sub 0 coming from the hypothesis test or the null hypothesis for proportions, h sub 0 should come from the null hypothesis for means. Our null hypothesis says the mean is equal to 45, so that's going to be our value here. We have our stats, so I'm going to make sure I go over to stats. I was in the wrong section, but I still should retain 45. And we have x bar and sx given to me in part B. We have 48.3, and we have 8.5. And our sample size, also is given to us at the beginning of the question, is 40. Lastly, our null hypothesis, we want to actually look at not equal to. So we're going to make sure that's checked. Now we can calculate this and get all the information, but I'm going to draw it instead, which should give us the same information as well. We're going to get the distribution that we should be able to draw, and I'm also going to know what the test statistic is, which keep in mind is going to be a t-test statistic, and I'm going to be able to get the p-value from this. So if you notice, this already shaded a small region down here, but since we're doing not equal to, this is going to be a two-tailed test, which means when I get to about the same distance on the right side, I get another shaded region. What we're going to find is our test statistic, t, 2.4554, that would be our test statistic, and our p-value is 0.0186. So with that in mind, we can do our test in a couple different ways. If you like to do the test using test statistic, where you see if our value is bigger than the test statistic, then that's good. Or if you want to do the p-value method, which I usually prefer, which is just checking if our p-value is less than our alpha level, then that's good as well. So, note that as well, like if you were drawing this t equals 2.4554, that will indicate the upper one here, 2.4554, but negative 2.4554 would be down here on the left side. So if you wanted to draw it more particularly. So we have B done. We calculate our test statistic. We have C done. This is the t distribution. Note it's centered at 0, so it's already adjusted. And D, we approximated the p-value. Now what we would interpret this is, again, as the likelihood of seeing something as extreme or more extreme than what we observed. We are assuming that the mean is equal to 45, but our mean was 48.3 from the sample. Now we wanted to see how extreme that would be compared to the mean of 45, and we find that there's about a 1.86 chance, according to my p-value there, of seeing something as extreme than what we saw, on either end in this case. Now, unfortunately, for E, the researcher wanted to test against alpha's 0.01, so they wanted to be very, very, very sure. In this case, unfortunately, our p-value does not beat that. Our p-value is larger than alpha 0.01, which means that it's not as significant as we would like. We have that it's a 1.86 chance of seeing something as extreme, but we wanted no more than 0.01. So we wanted something like 0.009 or something. This is too much. This is too big of an area of shading. So that means that we do not have enough information to reject the null hypothesis. And this is because our p-value is greater than alpha. If instead the researcher wanted to test against 0.05, then we would reject, because the p-value 0.0186 would be less than 0.05. So it always does depend on your alpha level. This one's close, but based on the alpha level provided, we don't have enough evidence. Lastly, to clean this up, I know this is a long video, but this is taking care of quite a few topics. Keep in mind that with t-test, you can also run it if you already have data. So I already went ahead and did this one. This one's not coming from a problem, just kind of demonstrating what this is doing. I randomly generated some numbers around 150 with some decimals above and below. And if you notice that I have a lot of values that are above 150, but some of them peak below it, of 149.98. I want to see if the information that I have here is enough to claim that my mean is actually greater than 150. And I have, if you go through the list that I have here, I think I have about 50 some values. Yeah. Most of them are above 150, but some are not. So what I'm going to do is go to stat, over to test, and we're going to run t-test because I have a list and I'm trying to find mean. Whoa. Something went wrong. Stat, we want to go over to test. Okay. In this case, we have our data, because I have the data in the list. And again, I don't want to go separately find the mean and standard deviation when this will already take care of that. I want to see if the information that I have in that list is enough evidence to claim that the mean is bigger than 150. So my hypothesis is that it's equal to 150, and I want to see if the information that I have shows that it's actually greater than that value. With my list, I'm just going to have that list 1 there. For frequency, there needs to be an input. You can't just delete this and move on. You need to put something here. If you do not have an actual list, then just for frequency, make sure you put a 1. If it's giving you problems, make sure that you're not in alpha or second or anything. If it's starting to flash A like this, you may need to hit alpha, so you can put in 1. This indicates that each value in list 1 is its own individual, that it only appears 1 time. With all that, we should be able to calculate or draw. I'm going to calculate. Should be able to read from there. So again, this is my alternative hypothesis. What I wanted to see is if the mean is actually bigger than 150. My t-test statistic is 3.86. That's a lot bigger than the last question was. And our p-value says 1.66 or 1.67. But keep in mind that at the end it says E-4. You need to be on the lookout for that. That means scientific notation. So take this decimal and move it to the left 4 decimal places, because this is the same thing as times 10 to the -4th. So what this really means is 0.0001667. So 0.000166. That is far less than 1%. It also calculates what the mean and standard deviation was from that sample as well as the size. So really based on whatever alpha level I would likely choose, which again is usually 0.1, 0.05, or 0.01, my p-value is smaller than all of those. My p-value is definitely smaller than 0.01 because this is 0.000166. That means that I have enough evidence here to reject that the null hypothesis is 150 and instead claim the alternative that the mean is in fact greater than 150. Keep in mind that even though this is a small difference, if you look at the sample mean is 150.04, that can be very important if you're doing something with engineering and need to make sure you don't waste materials or you're making something that doesn't fit a certain widget. So small changes like that can be very important, and this might highlight that some machine may need to be recalibrated. With that in mind, that's everything that I wanted to show you for how to do hypothesis testing on both proportions and on means. If you have any questions, feel free to put any questions in the comment section below, or if you're one of my students, just come up and talk to me. With that said, I will see you in another video.